Effective collaboration and 3D visualization with design rule checking requires 3D models for both electrical and mechanical. Expedition provides simple tools to assist with importing and aligning 3D models with cells. Model support includes these common file types: STEP, IGES, and SAT. Once imported, the model will appear with large green arrows around the part. This allows you to easily rotate the model in an X and Y axis. Now that we have our model in the correct rotation, we'll use intelligent pin snapping to finish aligning the part with the footprint. After selecting Align Pin Center, we select the mounting face of the pin, then the pad it will mate with to complete the alignment. This will move the part in the Z-axis and adjust the X and Y. With our 3D model assigned, we now need to update the library for future use. From the 3D toolbar, we can select Update Library. This will show all parts in the design that have new 3D model assignments. If replacing a model already assigned in the library, we can also set overwrite preferences. Lastly, Expedition allows you to check the entire design quickly for 3D mapping assignments. This can be helpful if you're not the originating designer. Placing parts in 2D only gives us part of the full placement picture, and placing parts in 3D may feel unnatural with our current knowledge of PCB. Expedition gives us the best of both worlds. We can tile a 2D and 3D, or have one on each monitor. This allows us to continue using familiar 2D space to position parts but take advantage of additional visualization and DRC provided with 3D. We'll show more of this in a short while. The real power of 3D visualization is having the ability to place parts around mechanical models. Our design has such requirements based on PCB mounting bracket and heatsink. As seen here, we've imported our mechanical model from a step file. From the mechanical model properties, we can rotate the part in all 3 axes and set coarse position values. To help with viewing later, we'll name the model and set its type. To place in its final position, we'll use intelligent mating operations, much like those in most MCAD tools. When placing our cursor near the hole in the MCAD model, a green line appears letting us know we've selected the axis. Next, we'll select the PCB mounting hole. Again, a green line gives us a visual. We now need to position this model in the Z-axis. Right-click and choose Snap to Faces. We'll then select the face around the top side of the hole, to which the bottom side of the board will mate. Lastly, rotating the PCB to the bottom view, we'll select the bottom face of the PCB. As mentioned before, with the MCAD model given a meaningful name and defined as mechanical, we can now control visibility, color, transparency of that object. To assist further with placement, Expedition allows you to set 3D DRC rules that are used real-time during placement. Let's set a component to mechanical model rule now that we've imported our PCB mount and heatsink. 2 rules can be created. Minimum, which is the absolute closest 2 objects can be placed without having issues during product usage and assembly. Optimum is a minimum distance that provides some buffer for either object to shift during product usage and assembly. Pulling an IC from the component navigator and placing in the lower left corner, we'll notice the PCB heatsink becomes visible in red, showing a collision between these 2 objects based on our design rules. As we move the part further away, the heatsink turns yellow, showing it below the optimum rule but more than the minimum. The heatsink was left invisible on purpose to help with placement. Making visible again shows placement would have been difficult from the top view. To fine-tune placement, we can move the part in 2D while viewing placement in DRCs in 3D. Lastly, we'll adjust the placement of our FETs and wire soldering holes for optimal placement. Using DRC checks is necessary to make sure our PCB can be manufactured and assembled properly, but these are based on minimum values. There are times when we need to know distances between 2 objects for other reasons. By using measuring capabilities in Expedition, we can check the distances between any 2 objects based on faces, edges, axis, or points. Before moving forward, we'll run a 3D batch DRC to verify rule adjustments have not created violations. From the Hazard Explorer add-in window, we can see 2 errors have been found. Investigating one of these shows Q2 is at a distance less than the minimum of 15 thousandths we set after these parts were placed. Selecting a notification shows the error. The fix will zoom in and move to Q1 while in 3D view. Notice both parts highlight in yellow when moving, indicating minimum optimum spacing. We'll move both Q1 and Q3 just outside the optimum distance. Running batch DRC again shows both errors and warnings have been fixed. At some point, we need to share data with internal or external resources. Aside from collaboration, here's some additional visual file sharing methods: TIFF, BMP, GIFs, JPEG, PNGs, 3D PDF, SAT files, and STEP. The most common 3D file sharing method is STEP. STEP can be generic or contain many elements. Expedition provides options to include all elements of the PCB as shown here, or minimal, depending on what you choose. For our example, we'll select component pads, metal, top and bottom, and via holes. As a quick view, we'll look at the exported STEP file in NX. Next, let's take a look at another common data format which contains some intelligence. It is very easy to share and anyone can view: 3D PDF. Again, from the export function, we'll choose the file type PDF. At this time, there are no options to set. Just set the file name and click OK. When opening a PDF that was properly created with 3D content, you're given full control over viewing, similar to Expedition in mechanical tools: zooming, rotating, shading, light direction, and cross sections. Expedition creates a very detailed 3D PDF, including pre-built tree with the following objects: mechanical, assemblies, board, components, component pads, planes, traces, and vias. As you can see, by expanding the component tree, we can find and highlight parts. Using checkboxes or selection from the right-click menu, you can hide or unhide objects. Here we are hiding the board area and turning on the PCB mount heatsink. We've covered several design techniques using 3D technology that allow us to design faster with higher quality the first time. Lastly, let's take a look at ECAD-MCAD collaboration. With a 3D window active, we can launch the collaboration app. This app provides several controls which allow us to determine what data can be imported or exported. Selecting the object filter icon opens a window giving us full control over the data we wish to export. Items like components, copper objects, board outline objects, keepouts, and fabrication objects can all be chosen. An added benefit to using NX for mechanical engineering is the ability to export 3D models used in our electrical design, saving time for the mechanical team and eliminating the logistics of dealing with model cross-reference files. Finally, we can send the data we've chosen. When we look at the history, we can see a record has been created for future reference. Moving over to NX, we will import the electrical data created by Expedition into a new assembly to be used with our master mechanical assembly. If needed, the mechanical engineer can make adjustments to part placement and send these changes back to Expedition for review. If accepted, those changes will be pushed to layout. If rejected, a response will be sent to the mechanical engineer to review, and the cycle repeats until the design meets all our requirements.